the last class we saw an example where you had two steps in a reaction, and first step is an electrochemical reaction, the second step is also an electrochemical reaction. And then we started with another example where you have one reaction which is electron transfer reaction, simple reaction, another reaction where there is an adsorption. Okay. So, I want to go through that, and if time permits I want to go through a reaction with two adsorbed intermediates. I want to go through another reaction called catalytic reaction. Okay. I do not think we will go through all of them today, probably today and the next 2 or 3 classes. Okay. I would like you to actually go through and derive the expressions. We will take you step by step. You also become more familiar with how to handle these mechanisms and propose a mechanism, derive the expression for it, and then get the expression for the impedance. Okay. So, what we saw in the last class is given in the top right. What we are going to see today is given in the left side on the top. We have a reaction P going to Q. P could be, for example, an electron transfer reaction between ferro and ferri redox couple, right. Then we have another material, anion is given by capital A, it is in solution phase. So, it is A minus in the solution phase, it sits on the surface, that means it is blocking the surface. Let us say this is the electrode, we have P in solution, Q in solution, we have A minus here, it can adsorb on the surface and release an electron. It can also take up an electron and come out into the solution. Okay. This P going to Q, we are going to assume right now that it is just one directional. We can also take the reversible reaction, it is just going to be a little more complex than this. Okay. And this can occur only on the free surface, that means any surface where A is adsorbed, it is not going to catalyze this reaction of P going to Q, only the surface which is free. So, if I take this surface and let us say this is the front face of this electrode, this is facing the solution, these areas we have A minus adsorb and releases an electron. So, it becomes A adsorbed. A adsorbed here means it is a bond between metal and A, this is how it looks like. In these locations we will not have this reaction happening. In other locations where bare metal is present, this reaction can happen. Okay. With that, I would like you to write the mass balance equation and the charge balance equation. We are going to call theta as the fractional surface coverage of the species, which is written in a shorthand as this. It is actually metal A adsorb. What happens when the first reaction proceeds? Does it alter the formation or does it create or deplete A adsorbed? A adsorbed is not even there. So, first reaction does not contribute to the formation of theta. Second reaction, forward reaction, that creates A adsorbed. Reverse reaction removes A adsorbed. Correct. So, if I want to say what is the rate of the forward reaction in the second reaction. So, this is K 2, this is K minus 2. So, I would like you to look at this situation, look at this condition and then visualize. Let us say these are all insulators, only this area, square area is visible to the electrolyte. In this electrolyte, we are going to say a particular fraction is already covered with A adsorbed species. The remaining material is available. So, if I want to write this in detail, whatever reaction I have written here in the shorthand as A solution, K 2 and K minus 2 forms A adsorbed and releases an electron. I should actually write a vacant site, and so A minus in the solution will go and sit on a vacant site and release an electron. Only then it is going to form, it is going to convert it to a site. So, it is going to increase theta. And when this A adsorbed species collects an electron, it goes out into solution as A minus solution and it releases this site, it becomes a bare metal site then. So, when the reverse reaction happens, bare metal site, number of bare metal sites will increase. When the forward reaction happens, it consumes the bare metal site, it consumes A minus solution. So, if it is an elementary reaction, we would write K2 concentration of the species A minus in solution. If that increases, you are going to have more of the forward rate, correct. Forward rate is going to be given by K2 1 minus theta concentration of A minus in solution. So, we are going to assume the following. We are going to say mass transfer is not rate limiting, we are going to say that the reaction when it happens, it is not going to alter the concentration of A minus in solution to a significant level. That is, we have a large tank with significant amount of A minus solution, P solution, Q solution, it is completely well mixed. So, in the electrode the reaction happens, but in the overall bulk the concentration change is not significant. We can measure the current, we can control the voltage, measure the current, we can control the current, measure the voltage, but by and large we are not altering the concentration of this species in the solution. That means, concentration of P, concentration of Q, concentration of A minus, all this in solutions are fixed numbers. That makes it a little easier to handle this. What are the units of K2? This rate is going to be moles per area per time, right. This is going to be moles per volume, it can be typically moles per liter, but we can convert this to moles per centimeter cube. Theta does not have any unit, K2 unit is going to be centimeters per second. Does it make sense? Okay. So, now I would like you to write the rate of the reverse reaction. I want to say the rate of increase in theta with respect to time, it is going to be, it is a C A solution is a constant for now. So, C subscript A, within that I am putting A minus solution, you can put it in a different way. Some of the publication will put this in a square bracket to indicate it is an activity which is also taken as a concentration, because activity coefficient is taken as 1 in these cases, minus. So, forward reaction will produce A adsorbed species, reverse reaction will consume it. What is going to be the rate of reverse reaction? K minus 2 theta. Now, K1, K2, K minus 2, will they depend on potential? All of them will depend on potential. So, we are going to write that as K2 is equal to K2 0 exponential and in our notation B minus 2 is going to be negative, or at least it can be 0, but it can't be positive number, because if I increase the potential the forward reaction will happen more. If I make it more positive, I am pulling out all the electrons from this electrode, therefore, forward reaction will become more, the first reaction will also become more, reverse reaction in the second reaction that will become less. So, K minus 2 will decrease with potential, K1 and K2 will increase with potential, which means B1, B2 and B minus 2 is going to be the negative side. These are not arbitrarily large numbers, they involve one electron transfer. So, these numbers are going to be given by alpha is the charge transfer coefficient, because number of electrons involved is 1, I am not showing it here, and alpha can vary between 0 to 1. So, at room temperature, this is of course universal gas constant R, at room temperature this is going to be around 38 or 39 inverse of voltages, with alpha being, if it is 0.5 it is going to be 19, something in that range, 19, 20, 18 if it is half, and B minus 2 is going to be, F is the Faraday constant, Coulomb per mole, R is the universal gas constant, T is the temperature in Kelvin. You can get these values from literature, you can get this from standard textbooks, just so that you know you can't put B1 as 1000 for example. It is not some any positive number, it has a physical meaning. For simplicity we are writing it in this notation. In literature sometimes you will find, or maybe many times you will find, instead of writing it as B1 they would write in terms of alpha, and the transfer coefficient of the first one they will call it as alpha 1, second one as alpha 2, etc.
Sir,
Yeah.
so the backward reaction won't happen if there are no electrons, right?
Yeah.
So why are we not adding that number of electrons in the equation?
The electrons influence the reaction by changing the rate constant, and the rate constant is proportional to the exponential of the potential. So, the electrons are accounted for in the rate constant through K, and the relationship is not, you can increase the electron, decrease the electron, we do not count the electrons, it is easier to measure the potential, and when you change the potential the rate constant actually changes. That is why whenever electron is involved in the reaction, we make the rate constant as a function of potential. When there is no electron transfer, we say it is independent of potential. So, you would like to write this as K2 theta into number of electrons. No, it does not work that way. It rather works by changing the K minus 2 or K2 here. We do account for it, it is just not that linearly increasing with this. Now, can you write the expression for the current? Faraday current. When I change the potential, how will the current change? So, when I change the potential, we know how the rate constant changes, that depends exponentially on the potential. But just because rate constant changes exponentially with potential does not mean the current that we measure will change exponentially with potential. The current is going to be given by, how much current can we expect from the first reaction? What is the number of moles of electron produced by the first reaction? Correct? Depends on the rate constant K1, which depends on potential of course. It depends on the concentration of P in solution. So, that is going to give us 1 electron, therefore, we are multiplying by 1, which means we are just leaving it as it is now. Second reaction has a forward and reverse reaction. Therefore, the current is going to be dependent on 3 terms here, K1, K2, K minus 2. It depends on the concentrations of P and A, which we assume to be fixed. It depends on theta. Theta will vary with potential. Therefore, the current in general will not be exponentially changing with potential. The rate constant still, we assume that they change exponentially with potential. So, when you are given the reaction, you should be able to write the Faraday current for this, you should be able to write the mass balance equation for this, and you should be able to write the steady state surface coverage. That means, can you write the expression for theta SS? When I want to set this to 0, that means DC potential is applied, there is no change of theta, there is no change of potential with respect to time. I am going to get K2 as K2 DC, K1 as K1 DC, but it does not participate in this, it does not come into play here. K minus 2 DC, can I write theta SS? Is that correct? This is theta steady state. Here both K2 and K minus 2 depend on potential. If I increase potential, K2 will increase, K minus 2 will decrease. When you practice, when you are given a new mechanism, first thing you do is to write the mass balance, then charge balance, write the steady state expression for the surface coverage. You can write the steady state value for the Faraday current, that will give you polarization curve. That is, if you go to potential and wait there, if you scan it at a very slow rate, what is a slow rate? That depends on the system, but if you go at 1 millivolts per second, half millivolt per second, 2 millivolts per second, many times you will not see any difference between those data, then you would say these are okay. No, the contribution from double layer charging is negligible and pretty much everything happens because of the reaction. Then you would get a polarization curve. If you propose a mechanism, first the polarization curve given by the model and polarization curve that you obtain from experiment, they should match within the experimental error, within the noise level. Yeah. This is the first part. So, all of you are able to get the theta SS. Next, we have to linearize this. To get the impedance, I have to linearize this. That means, first I have to expand this as potential as EDC plus EAC, where EAC is EAC 0 sin omega t. That means, K1 will be approximately and likewise K minus 2 is going to be approximately equal to K minus 2 DC multiplied by 1 plus B minus 2 EAC. The right way is you have to write the entire thing in Taylor series, truncate it after the second term and then get here. When we do it frequently, we can directly write this approximate expression. If I expand K1, K2, K minus 2, I also have to expand the theta. I am going to say concentration of A and P solution are constants, therefore, I am not going to worry about that. I will get an expression which says K1 can be expanded as K1 DC plus B1 K1 DC EAC. So, this would contribute to the Faraday current at DC condition, this would contribute to the IF AC. Similarly, K2, I am going to write it as K2 DC C minus solution 1 minus theta SS plus B2 K2 DC C minus solution 1 minus theta SS EAC. See, if you remember, K2 is expanded and then truncated, so you would get two terms there. Theta would be expanded and truncated, you would get two terms there. And when we multiply, we are going to get one constant, two EAC term, one EAC square, which we are going to neglect. So, out of the 4 terms, we are going to keep one DC term, we are going to get 2 AC terms. So, this is the DC term here, the next is the AC term, and then one more is going to be an AC term there. So, this Faraday current expression, the way it is written, it has 1, 2, 3 terms. The first term is expanded, there is no theta there, it just gives you 2 terms there. Second term has K2 and theta. So, you would get 4 terms, out of which we throw away 1, we have 3 terms. So, 1, 2, 3 comes here. Third term has K minus 2 and theta, again we would expect 2 multiplied by 2 to give us 4 terms, out of which we are going to keep 3 terms, but please do write it down. Now, you can always copy from the board, but if you write it, even if you make mistakes, it is fine, you can check with the expressions here and then correct it. This way you would actually learn how to handle it. So, I got the third term should be minus and then expand the entire product of k minus 2 theta as k minus 2 dc theta ss, that is the dc term, b minus 2 k minus 2 dc theta ss EAC, then k minus 2 dc d theta by de EAC and then EAC square term which goes away. I can rearrange all this. I got 1, 2, 3, 4, 5, 6, 7, 8 terms here. 3 of the terms contribute to DC. Then remaining 6 terms, am I doing it correctly? Am I missing anything? I got 1 d theta, another d theta. Yeah, out of the 8 terms, 3 terms go to the DC, 5 terms go to the AC. Out of the 5 terms, 2 of them depend on d theta by dE, remaining 3 terms are independent of d theta by dE. That means, when you do the impedance spectra, when you measure the impedance spectrum, when you apply different frequencies, the 3 terms here do not depend on frequency. The term here d theta by dE will depend on frequency, that we are going to derive later, but right now just take it for granted that d theta by dE will depend on frequency, and when we apply infinite frequency, very high frequency, d theta by dE will go to 0. That means, if you apply very high frequency AC potential, then potential changes very quickly, the rate constant will change very quickly, surface coverage cannot keep up with that, it cannot change that much. So, it is going to be negligible. Change in surface coverage with respect to potential, change in surface coverage with respect to time will be close to 0, when theoretically if we say infinite frequency we will get 0 here. That means, this is the part that remains if frequency is very high. This parts will go to 0 when frequency is very high. This entire box here is IF AC, the top box here is the DC current. Is everyone okay with this? Can you check and make sure it's what I written here is fine? Now, I would like you to think and tell me what would happen to the DC current, what would happen to the steady state surface coverage theta when potential is increased. You have the expression for theta under steady state condition, you have the expression for Faraday current under steady state condition. For a given A minus solution concentration, if I increase potential, what happens to K2? Increases. What happens to K minus 2? Decreases. So, if I have large potential, this becomes very small, this becomes large, this also becomes large. We are fixing the A minus solution concentration anyway. Therefore, theta SS will approach 1 when DC potential is increased. When DC potential is decreased, what happens? K minus 2 will increase, K2 in the numerator and denominator, that term will decrease. So, when DC potential is moved to negative values, theta steady state will approach 0. It will not become 0, it will become close to 0. So, I would expect to be like an S shaped curve, where that slope occurs depends on the parameter values and the concentration values, but the slope will occur at some location. Very large potential it is going to be close to 1, very small potential it is going to be close to 0, anything in between it is going to be a value between 0 to 1. Now, what happens to the Faraday current? Just the DC Faraday current, not the, I am not looking at the AC yet. DC part is given by this top in the box. What I written is actually not correct. Can you identify a problem here? first reaction can happen only on the bare metal surface. Is that correct? Therefore, if the entire surface is covered by A adsorbed, you will not get any reaction, any significant amount of reaction in the first step. So, the current is actually going to be given by DC, correct? So, please do not blindly copy what I write here. Theta SS is still okay. The theta equation, mass balance equation is still okay. First reaction does not contribute to the mass balance equation, right. But the Faraday current and the expansion Taylor series, truncation that we got, all of them are not correct. So, please do rewrite it now.
Sir,
yeah.
Can you explain why first reaction cannot happen completely? The reaction is happening in the solution, right?
Reaction happens on the electrode surface. The reactants and product are in solution. So, the reactant comes, sits on the bare metal, not for sufficient time to be considered as an adsorbed species. As long as it touches the bare metal, it becomes the product Q and then comes into solution.
That mechanism should be mentioned, right? Without mentioning, we cannot know.
We did mention it. We did say if you have a surface like this surface is covered, the reaction, first reaction can happen only on the bare metal. Second reaction, forward reaction can happen only on the bare metal. Reverse reaction of course happens only from the adsorbed species. But first reaction does not contribute to increasing or decreasing A adsorbed. It can happen on the bare metal. I think I mentioned that. Now, with little more complex expression, you will have to derive that for AC, but before that I would like you to check what will happen to the Faraday current when potential is large. When potential is large, theta becomes close to 1, K1 becomes a large number, K2 becomes a large number, correct. K minus 2 becomes a small number. So, as E DC increases, K1 and K2 increases, K minus 2 decreases, theta increases, 1 minus theta will tend towards 0. So, K1 will increase, Cp of course remains constant, 1 minus theta will tend to 0, the product of that will tend towards 0. You should not believe me, you should actually try that and see. K2 1 minus theta will tend towards 0. See, theta is given by K2 Ca minus solution at any given DC by K2 DC Ca minus solution plus K minus 2 DC. So, 1 minus theta is going to be given by K minus 2 DC by this number, correct.
So, but the rate constant says that if we are increasing the value of K2, so we are saying that we are increasing the second reaction, rate of reaction, we are making it faster. So, if that reaction is getting faster, then previous one will automatically not get faster, because you said that electrons will if the electrons are participating in any reaction,
yes,
the rate constant depends on potential.
Yes.
And if the potential of that thing is increasing, so that simultaneously it will increase.
Rate constant is increasing, we are not denying that.
Yeah, but I am saying that increasing the second potential reaction, potential of second reaction, simultaneously, so it means we are increasing the potential of the whole system.
Yeah, increasing.
So
We are increasing the potential of the electrode.
Yeah.
Therefore, K1 will increase, K2 will increase, K minus 2 will decrease.
K minus 2 will decrease because of the negative.
It's a electron is participating in the reaction as a reactant for K minus 2. For K2 it is a product, for K1 it is a product. So, when I increase potential I am pulling out the electron. When I am pulling out the electron, I will facilitate the forward reaction.
Okay, so if I say theoretically, if we go with this one that you said that if we increase the value of K2 and decrease the value of K minus 2, so we are increasing.
We are increasing potential, therefore K2 increases and K minus 2 decreases.
That's the thing.
Yeah.
I mean, so how this theta will increase? So theta must decrease now. So because theta says that how much of space is available for the
Theta is steady state theta, correct. We took the mass balance equation, which was correct anyway, and then derived this. Now, what happens when potential is increasing? Forget the K1, K1 is not here. Okay. Concentration of A in solution is fixed number. K2 is going to increase. K2 in the numerator and denominator is going to increase, K minus 2 is going to decrease. So, it is going to become almost close to 1, because numerator and denominator are large numbers, equal, more or less equal. Therefore, as EDC increases, theta will tend towards 1. Here I say it increases, I should say it tend towards 1. If theta tends to 1, 1 minus theta will tend to 0. So, what happens is when I increase potential, more and more of A minus solution species adsorbs on the surface. But as it adsorbs, vacant metal site become, number of vacant metal site becomes fewer. That means the rate of that reaction will not increase, K2 will increase, but the rate will not increase, because the rate is given by K2 Ca solution 1 minus theta. Rate of the first reaction is K1 Cp solution 1 minus theta. We will take this factor out, it is a constant. How does K1 1 minus theta change? 1 minus theta is K minus 2 dc given by this number, correct. Theta is here, you can do the algebra and prove that 1 minus theta is this expression here. K2 into 1 minus theta is going to be K2 dc. In fact, we will keep the Ca. The rate of the second reaction is K2 Ca solution, correct. I am going to call this as A, this as B. So, it is basically AB by A plus B, yes. Okay. Now, when I increase the potential, put realistic values for this and check the values. Theta will tend towards 0. Of course, it may be possible that for certain values of K minus 2 and the value of K2, K2 0, K minus 2 0, B 1, B 2, it may not happen that easily, that early, but I will have to check the values. For the values we have tried, we find that it fully covers the surface. Once it fully covers the surface, the reaction rate is basically reduced.
Here theta means we are talking about the space available for the reaction.
1 minus theta is the space available for reaction. Theta is the space of the A adsorbed. So, what would happen is, when you have a large potential, K2 is increasing. So, 1 by K2 will decrease, becomes a small number, 1 by K minus 2 will become a large number. One of them is going to be large, one of them is going to be small. I can ignore the small number, keep the large number. So, if this is a large number, 1 by a large number is going to go towards 0. So, 1 minus theta will go towards 0. In fact, for I think any realistic parameter value, K2 0 has to be a positive number, any realistic parameter value, and B minus 2 is negative number, we would get theta as going towards 1, 1 minus theta is going towards 0, and the rate of the second reaction will go towards 0.
So, can we say that the increasing the value of K2 and K minus 2 results in more in the resistance in the system? Because according to the formula
No, wait, increasing the value of K2 and K1. You can't increase the value of K2 and K minus 2 simultaneously.
I am decreasing it.
Yeah.
Because we are proving that theta is increasing as we increase the K2 and K minus 2 we decrease.
Wait. We are not saying that any small change in potential from any value will give this. When potential is very large, K1 DC is going to be very large. K2 is going to be very large and K minus 2 dc is going to be very small. Under those conditions, we are showing that the surface is fully covered by adsorbed. Rate of the reaction has, you can have the current here written in 3 terms. When theta is going towards 1, but K minus 2 is very small, this product will become tend towards 0. The second step forward reaction, K2 Ca solution 1 minus theta, we can show that it tends towards 0. First step is going to be K1 Cp solution 1 minus theta, and 1 minus theta is this term, K1 dc Cp solution is here. Here also we can divide by a similar expression. Let us see if I can get enough space here. Let us divide by the factor K2 dc, Ca minus solution, K minus 2 dc. Numerator you are going to get K1 dc by K2 dc, Cp solution by Ca minus solution. Denominator you are going to get 1 by K minus 2 dc, 1 by K2 dc Ca solution. Correct.
So by changing the values, we are maintaining the current in the system.
No, we are not maintaining the current in the system. We are just increasing the potential to a large value and observing the response. Here we are predicting the response. The response here, it has 3 contributions: contribution from the first reaction, contribution from the second reaction forward and reverse. Second reaction, forward reaction will give rise to more or less 0 current. Reverse reaction will give rise to more or less 0 current. First reaction, how much current is it going to give us? That is what we are finding here. So, the expression is going to be K1 Cp solution 1 minus theta. We have the expression for 1 minus theta, multiply by K1 Cp solution under DC condition. We have expression for 1 minus theta steady state. So, if you multiply by this, this is the expression you get. Of course, you have a factor of Faraday constant there. Divide by this expression K2 dc Ca solution, K minus 2 dc, the entire product, divide by this, you are going to get K minus 2 dc here, you are going to get K2 dc Ca minus solution here. Numerator is going to be K1 dc by K2 dc, whatever terms we get here. Is that okay? You know how we got this?
I got it. I got this point, that how we got this, but I am not getting the point that we are maintaining the current.
We are not maintaining the current.
We are getting more current.
We are going to find whether we will get more current, less current, how much current we are going to get.
We have already said it that by increasing the value of K2 and decreasing the value of K minus 2, we are providing more potential.
We are providing more potential. It does not mean we will get more current.
That's what I am saying. Now, if we are decreasing the current, so we are increasing.
We are not increasing the current, we are not decreasing the current, we are changing the potential. We are going to find what will happen to the current.
But
How do you know that current is going to decrease or increase?
I don't know. I am just saying here. We know that V is equal to IR. So
No.
changing the
V equal to IR when you have a resistance.
That's what I said.
We don't have a resistance. We have an electrochemical reaction.
But if something is absorbed, something maybe there is a possibility that that adsorbed layer may create a resistance.
Why are you imagining that? When you have a reaction, it will not act as a simple resistor in most of the cases. It will act as a resistance in parallel with the resistance and capacitance, for example, and the resistance value you get may be negative. You can't think it's a electron is passing through this adsorbed species, it's just sitting there as a conducting medium. It doesn't happen that way. When you give potential, you have more reaction or less reaction, and that causes the current to change. When you get an electron here, you get current. So, what we are measuring here is the current because of the reaction, and it cannot be modeled in general by a resistor. So, the example is taken here specifically to show that you can increase the potential and you will see a decrease in current. So, you can't make a conclusion beforehand and then say I want the current to decrease, show me how the current will decrease, or I want the current to increase, show me how the current will increase. So, this reaction does not represent a resistor. When you change the potential, whatever happens to this expression here, that tells you how much the current is going to be. We are looking at it one term by another term, one by one we are looking at these terms. So, when you go to large potential, third term goes to 0. When you go to large potential, second term goes to 0. When you go to large potential, what happens to the first term? We are just analyzing it now. Correct. This is of course a constant number. This is also a constant number. This number, when you look at the value here, when I increase the potential, what happens to k minus 2 dc? Becomes a very small number. This becomes a large number, I can neglect that. When the number here is large, 1 by that number is going to be negligible. So, this is approximately equal to k1 0 by k2 0. This k minus 2 dc comes to the numerator, k minus 2 dc, k minus 2 0 e power b 1 minus b 2 plus b minus 2 e dc. Of course, I am leaving out the other terms, Cp solution, Ca solution, etc. I should write them down. So, this is approximately equal to e power b 1 minus b 2 plus b minus 2. Remember, b minus 2 is negative, b 2 is positive, b 1 is positive. Now, if this term is negative, current will go to 0 at large EDC. If this term is positive, first term will not go to 0. Does it make sense? Basically, I am evaluating what will happen to the first term when EDC increases. For the second term and third term, definitely they will go towards 0. First term, under certain conditions, it will go towards 0. If b 1 is greater than b 2, it will definitely go to 0. Sorry, if b 1 is less than b 2. If b 1 minus b 2 plus b minus 2, which is a negative number, if sum of this becomes a negative number, this will go towards 0. Under that condition, you can tell the DC current, Faraday current will tend towards 0 when EDC is increased to a large value. I am not saying from 0.2 volts to 0.3 volts. We have to really find how it is. When it is very large, it is going to be tending towards 0. When it is very small, what will happen? Very small meaning, I do not mean it is 0, it can be negative value. EDC can be negative. With respect to the equilibrium potential, if we are at equilibrium, then EDC is 0. If you are well below equilibrium potential, EDC is a large negative number. When it is large negative number, K1 decreases, K2 decreases, theta axis tends towards 0. Under those conditions, K1 decreases, theta will tend towards 0, this is a constant. So, the first term will go towards 0. Because K1 is very low, this is a constant, this at the max it will be 1, first term goes to 0, second term also goes to 0. We have to look at the third term. Sorry, Ca solution. You can divide the numerator and denominator by the entire expression given in the numerator, and you can show that this value will go towards 0. when potential is very low, this current will go to 0. When potential is large, under certain conditions current will go to 0. In between it is going to have a value, it is a continuous function. Large EDC it is 0, low EDC it is 0, in between it is going to increase and decrease, only then you can make sure it is a continuous function. It has actually multiple derivatives, so it is not a function with kinks, it is going to show at least maximum. Okay. Now, you can convince yourself by taking actual values. Given the expression for theta, given the expression for current, of course, to look at the impedance we need to get d theta values, we will see tomorrow. But theta versus DC and current versus DC for some specific values of constants. If we take them, this is the plot that we get. At low values it is 0, at large values, large here in this example is 0.5 volts, low here is close to 0. Okay. Of course, when it goes to negative values, P going to Q is going to be a reversible reaction, unless there is no Q in the solution at all and we are taking it out as soon as it is formed. If you have both P and Q in the solution, you will have to consider the reverse reaction also. Right now we are not considering it, we are going to say we will go from 0 to positive values and look at it. Current goes from 0 to a peak value and then comes back to 0 value or close to 0 value. Okay. And of course, we are going to derive the expression for impedance. What I want to show you is for this set of parameters at 0.1 volt and at little larger potential. If I take impedance at this location and another location here, one time I am going to get two capacitance loops with the second loop on the right side, another time I am going to get capacitance loop with it coming on the negative side. It is quite possible for this to arise and we can explain why it happens this way. You have negative impedance, you can show that this model will give you negative impedance, you can say why does it become negative. Physically, what can I say about the reaction? Why does it become negative? Why does it appear to show a negative impedance? It is not showing negative impedance in the sense when I give potential, increase the potential. If I go here, look at this location. When I increase the potential, what happens to the current? It increases or decreases? Decreases. That means if I apply a sinusoidal potential, this is the time, this is the potential. I am not at 0. This value is close to 0.3 volts. This may be 0.305, this may be 0.295. I am applying 5 millivolts amplitude. Current will decrease and then increase. When potential increases and decreases, current here is going to be some value, it is 3 milliamp. Let us just make up that number and say it is 3 milliamps. It is going to decrease and then increase. Whenever this increases, current is going to decrease. And whenever this decreases, potential decreases, current is going to show an increase. It has a 180-degree phase offset. It does not mean when I apply a positive potential here and negative potential here, electrons are still going to travel from this direction to this direction only. But only thing is when I increase the potential, less or fewer number of electrons are traveling. When I decrease the potential, more number of electrons are traveling. So, it is a negative differential impedance, not negative resistance where I give voltage like this and current actually flows in the opposite direction. That is not the meaning of this negative impedance that you observe. When you measure in experiment, when you apply sinusoidal potential and measure the impedance, we are only measuring the differential impedance, that is we are measuring the amplitude ratio and the phase difference between the potential and the current. Okay, we will stop here today.